All right, welcome back everyone. Now, due to popular demand, I am going to be exponentiating a matrix today. I'm going to show you how that works. And when I say popular demand, I mean my family said it would be cool, so I'm going to do it. So hopefully you enjoy this, family. So what we need to first establish from the start, before we even begin to exponentiate a matrix, we have to define a matrix composed of eigenvectors. Mainly, there's a claim I'm going to establish, but first I'm just going to say it. So a matrix composed of unit eigenvectors is an orthogonal matrix. And that may seem like just a bunch of words, but we're going to map some of these definitions to the words that I'm saying and get into it quantitatively. But if you are unfamiliar with what an eigenvector is, to sort of put it succinctly, an eigenvector is just any vector, say just in any particular arbitrary direction, that is scaled up, that basically has a property whereby it is scaled up by some scalar quantity we'll call lambda. And what happens whenever you apply this scalar quantity, when you multiply the vector, the eigenvector, by this eigenvalue, it retains its orientation. It keeps a linear path within the eigenspace that it is defined in. So that's essentially the idea of what an eigenvector is. That whole concept all alone deserves a video in and of itself. But for now, hopefully that gives you a little bit of an idea as to what an eigenvector is. So let me get rid of this and let's keep going. So first, what we need to do is verify the claim I had already made, that an eigenvector matrix composed of unit eigenvectors is an orthogonal matrix. So let's define some eigenvectors, some unit eigenvectors from the start, okay? So we're going to have some E, so E hat 1, which is going to be our unit eigenvector, is equal to 1 over the square root of 2 with 1 and 1, represented as this sort of column vector, basically. And then we're going to have a second eigenvector, which will be 1 over the square root of 2, and we got 1 and negative 1 for the column. Okay, so we have our two eigenvectors normalized with this sort of coefficient up front. And what we want to do is put it into a matrix, okay? So what we want to do here, we'll say some M matrix we'll call equal to, we have E hat 1 times E hat 2. Oh, bracket that off. So now what we can do is basically express this collectively. So what we have now is this equal to 1 over the square root of 2, where our matrix is now 1, 1, 1, negative 1. You can kind of just think of it as sort of pushing these two column vectors together, and it gives you this symmetric 4x4 matrix. Okay? So now, to verify orthogonality, we have to multiply said matrix by its inverse, or its transpose. So what we can do here is take the transpose of this matrix, where I like to think of it as sort of aligning my hand horizontally with the top row, and then sort of orienting it 90 degrees, and that tells you how to swap the rows and the columns. So we're going to have M transpose, which now is basically represented like so. We're going to have E hat 1 and then E hat 2, right? Okay, cool. So fortunately for us, we have a symmetric matrix, meaning it is equivalent to what we have here. If you swap the columns and the rows, it's just going to give you the same exact quantity here. So we're going to have 1 over the square root of 2, where we have 1, 1, 1, negative 1. All right. So now what we want to do is basically just multiply these two together. So let's do M times M transpose. And now, to ensure orthogonality, to sort of check that sort of criteria, what we have to achieve here by multiplying these two together is the identity matrix. It's supposed to output the identity matrix. If you multiply a matrix by its transpose and you get the identity matrix, then you know it's orthogonal. Okay, so let's do that. So multiplying these two together, we're going to have 1 over 2, and we're going to have 1, 1, 1, negative 1, and then 1, 1, 1, negative 1. Okay, so multiplying, not too terribly difficult. What we get by just basically pouring the first row into the first column, we get, let's see, we have 1 over 2 once again. So we're going to have 1 times 1 plus 1 is 2, and then 1 times 1 plus negative 1 is 0. And then once again, 1 times 1 plus negative 1 times 1 is 0. And then, yet again, we have 1 times 1 plus negative 1 times negative 1, which is 2. And lo and behold, when we take that scalar quantity, multiply that out, we just get the identity matrix. Cool. So, verified. We know that this is orthogonal. So, now what we want to do is define now that we've defined the orthogonality of an eigenvector matrix, we want to define the eigenvalue problem in terms of matrices. So let's clear some of this out, and we're going to start going through the eigenvalue problem and defining what is known as the similarity transformation. Okay? Okay, so now we have our eigenvalue problem defined here in terms of our matrices. So we have some matrix multiplied by our eigenvector, our state vector, if you want to use the jargon in quantum mechanics, which maybe one day we'll start getting a little bit more in depth with. But for now, we have our matrix multiplied by our eigenvector normalized, so represented as this row matrix is equal to some eigenvector, some eigenvalue indexed to an arbitrary amount of eigenvector values multiplied by our eigenvector matrix. Okay, so now since we've already seen that the transpose of this eigenvector matrix is also represented as a column matrix, we can express it once again. We have E. So our eigenvector matrix can be expressed, or it is defined to be, as a column matrix of a bunch of eigenvectors. Okay, so we're going to have E hat 1. Let's make more room here. And then we're going to have E hat 2, and that just kind of goes to some arbitrary amount of values here. Okay, so E hat n. Let's write it like that. All right. So now we can express this similarly. So when we have this, we have, say, m times E hat I. Well, if we're just multiplying some arbitrary matrix by our eigenvectors, well, since it can be defined as a column matrix, we can represent it like so. So we basically just have m E hat 1, and then we have m E hat 2, and that just kind of goes to some arbitrary length. And let's make this look better. All right, so we can define it like so. Okay, so now since we have defined in this instance our eigenvector matrix as a column matrix, we have to apply that to the other side, the right hand side here. So we're going to have some lambda value multiply, so lambda 1, or our eigenvalue, multiplied by E hat 1, and then I think you see where this is going, so we're going to have lambda 2, E hat 2, and that just keeps going. Okay, so lambda n, E hat n. Let's parentheses this off. All right. Okay, so now that we have defined our matrix in this way, what we can do now with this right-hand side is effectively extract, or rather factor out all of these eigenvalues as a diagonal matrix. Okay, so what we get here now is some diagonal matrix where we have lambda 1, lambda 2, lambda sub n. All right, and then once again we're just going to have e hat 1, e hat 2, and then e hat n. Great. So now we can express this a little bit more compactly as just some matrix elements here. So what we have is basically what we have defined to be our eigenvalue problem now. Since we have a diagonal matrix, we can express lambda a little bit differently. So we're going to have m. I'm just going to drop basically the hat and the I, but hopefully you can get the picture here. So we have our matrix times our eigenvector matrix is equal to, we're going to capitalize our lambda to indicate a diagonal matrix of eigenvalues, and then we're going to have E. Great. So what we have here is a very important description, a very important equation. It is known as a similarity transformation. It's a way of transforming from one orthonormal basis to, or if you have an orthonormal basis, you can transform into, say, another orthonormal basis, which is basically the definition of an orthogonal transformation. Okay, so in that way, that allows us to express things such as like rotations or reflections in space. So it's very, very useful to have this definition. It may not seem like it immediately, but hopefully that will be made clear a little bit later. But this is the bread and butter of what is needed to calculate, or rather to exponentiate a matrix. Okay, so we can sort of represent this a little bit differently. So we can basically bring our eigenvector matrix to the other side, and we're going to have E inverse, so e to the negative 1 times m E equals lambda. Okay, so we have our similarity transformation, and it is also important to note that this really only works with symmetric square matrices. And if we have a symmetric matrix, that means we can express our inverted matrix here as E transpose. So this can also be written as E transpose m E lambda. Okay, so we have our similarity transformation, and we have the tools necessary to exponentiate a matrix now. So let's start doing that. So what we need to show right off the bat is what it even looks like to exponentiate a matrix. So what we have here is E to some matrix, some arbitrary matrix. So E to the m. It's still such a weird, anomalous sort of representation to even think that exponentiating a matrix is like feasible or a mathematical tool that warrants further analysis. But as we'll see later, there's some very, very valuable sort of reasons why you would need to exponentiate a matrix. So now what we can do here is define this in terms of its Taylor series polynomial. Okay, so we can basically expand this out and represent it in its sort of summation form. So what we have here is a sum of some n value right here, and that'll go to infinity. And what we have is, so basically we take m, raise it to the nth power over n factorial. All right, so here now we have something we can work with. Okay, so how can we let's isolate this m matrix to the nth power and see what we can do with that. What is that? Say we have m to the n, right? All right, so how can we define this? Well, what we can do is reach into our toolbox and bring our similarity transformation and start expressing our matrix in a similar sort of form here. Now, if we were to raise this to the nth power, well, let's say now that we are solving for m, basically, let's bring all of this over. So we can actually express our similarity transformation as m is equal to E inverse times our diagonal matrix times our eigenvector matrix, okay? So let's raise this to the nth power, right? So we're just going to be multiplying these all out here. So we're going to have m to the n, and we're going to have, so basically E inverse times our eigenvalue diagonal matrix and E to the nth power. All right, so let's just carry out the operation and see where this takes us. So we're going to have E to the negative 1 times lambda, capital E, right? And we're going to multiply that by another one, okay? And you kind of get the picture here where this is going, or maybe not, but we'll see. So that goes to an arbitrary nth amount of values, and we're going to have E to the negative 1 lambda E. Okay, so what we can see here right off the bat is the matrices that are adjacent from one another, E and E to the negative 1, they're just going to give us the identity matrix. They're just going to be 1, which is great. These will cancel out for all sort of inner eigenvector matrices. So these will all cancel. And what we're left with at this point is that now m to the n is equal to just E inverse times our diagonal matrix to the nth power multiplied by E. And this is exactly what we need. So now what we can do is re-express our Taylor series polynomial in terms of our diagonal matrix, okay? So this is kind of where we can actually start working with something, because computing a diagonal matrix, such as just a bunch of eigenvalues, it's utterly trivial. So what we can do now is express that like so. So remember, these aren't raised to the nth power, but so we'll have those on the outer points. So E to the negative 1, and we're going to have a matrix, right? A matrix of basically Taylor polynomials, okay? So we're going to have our summation across an infinite number of elements, and it's important to note this is 0, I think. Yeah, so we're going to start out at 0, but nevertheless, we're not going to be expanding it too much here. So what we now have, since what I'm going to do is factor out this polynomial, and what we're left with is just this. So our diagonal matrix to the nth power times our eigenvector matrix, okay? And, let's write this out a little bit more thoroughly so it becomes a little bit more clear. So E to the negative 1, and what we're going to have here is our summation across an infinite number of elements, and we're going to have lambda 1, lambda 2, that is not a lambda n, okay? So that's just going to keep going n times. Okay, and now that is going to be multiplied by our eigenvector matrix. So great, now we can very clearly see how this radically simplifies the computations involved here, because this would be just horrible to just take a bunch of matrix elements and multiply them out like n times. That's a very, very unproductive use of your time. If you're having to multiply like the same matrix by itself n times, that's going to take a while, and because matrix multiplication can be a little tedious, especially if you're dealing with either complex numbers or things that are not well defined, or you have just a bunch of just very ugly numbers to work with, it gets a little tedious. But this radically simplifies anything. So what this says is to compute the exponential of a matrix, all you really need to do is find the eigenvector of whatever matrix you're trying to exponentiate, find its eigenvector, compute its eigenvalues, or rather, you would compute its eigenvalues and then its eigenvectors. And once you have those, you'll more easily be able to exponentiate it, because once you have those values, it's just trivial. All right, so let's sort of write this out a little bit differently in case it's not clear yet. So we're going to have e to the negative 1, and this basically just ends up being e to the lambda 1, e to the lambda 2, e to the lambda n times e. And there we go. All you're really doing is taking e, raising your eigenvalues n times, and then just multiplying this out. And it's pretty easy. So let's go through a little bit of an example. I'm not going to exponentiate explicitly any matrices here. However, I'm going to show you where this comes up and when it becomes very useful to understand and know how to do this. So let me clear some of this up. All right, so what we have here now is the time-dependent Schrodinger equation. And if you'll recall in my last video, what I did was apply the separation of variables method to solve for the time-dependent Schrodinger equation in under 2 minutes. But this time I'm going to sort of be a little bit more methodical about just the purpose and why exponentiating a matrix becomes very useful here. And you might already know if you've watched the last video, but let me sort of break it down. So, at least in the framework of quantum mechanics, matrix arithmetic was originally the sort of bread and butter of quantum mechanics. In fact, it was originally regarded as matrix mechanics. And the reason why that is because if you're dealing with like mutually exclusive states or operators that don't commute or observables that don't commute, it's very useful to sort of put that in the frame of matrix multiplication, because matrix multiplication isn't commutative, meaning the order in which you apply the operations matters. So this is a little bit of an interesting example, I personally think, at least as to why matrix exponentiating a matrix becomes a very valuable tool here. So we're gonna solve it how I did before, but I'm just gonna be a little bit more methodical about it. So now, what we want to do is basically rearrange this and apply our separation of variable, okay? So what that leaves us with, if we sort of rearrange this a bit, we're going to have d, where am I at? So d psi, and what we're going to do is I'm going to bring this dt over to the other side. I'm going to bring our psi matrix over to this side, and we're going to have psi. Okay, and we're going to bring that over. So if I divide that out, but I'm going to change the I value to, I'm going to move it to the numerator. So we're going to have negative I over h bar times our Hamiltonian, and that is going to be multiplied by dt. Okay, now all we really need to do at this point is integrate both sides. Okay. So if we integrate, well, what we get here is the natural log of psi here. And this, on the other side, just gives us negative I over h bar, since we're dealing with constants here. So, we're going to have our Hamiltonian multiplied by t. Okay, and it's also, we have some constant of integration that we have to tack on there. We'll call it a. Alright, so now all we really need to do is exponentiate both sides, and I assume you probably can see where this is going now. So if I exponentiate both sides, this just becomes, so you're going to have psi, and psi is going to be a function of t here. And because remember, time-dependent Schrodinger equation. And for exponentiating both sides, well, basically what we end up with is this a term can be sort of decomposed from our exponent, effectively. And because basically what I'm doing is exponentiating this, and because of because of the exponent rules, what we can do is sort of pull that out, and what we just have is e to the a, which is just another constant. Okay, so we're going to have a times e to the negative I over h bar times our Hamiltonian multiplied by t. And there we go. That's basically all there is to it. You can see here quite clearly we are exponentiating our Hamiltonian matrix. And to actually go through with that operation, it's incredibly valuable to know the similarity transformation that we just used previously. So that's basically it. I hope you thought this was at least somewhat interesting. I know I thought it was just utterly abstract and wild when I first learned about it, and it's even better to know that it's rooted in some very practical situations here. So, well, thanks again for watching, and stay tuned for my upcoming video, whatever that may be.